Hi guys, welcome to this revision summary video looking at types of substance, in particular ionic, covalent and metallic bonding. The aim for this video is to look at all the key things that you need to revise to get yourself ready for the exam. If you want to go into more detail on any particular part, I've put a link in the top right hand corner to the playlist which goes into each section of the video in more detail, including practice questions and the model answers for them. So this is just an overview. If you want more detail, have a look at the playlist in the top right hand corner. The first section of this summary video then is going to show you how you can work out if any substance is ionic, covalent or metallic. Now nice and simply, if it's ionic, it contains a metal and it contains a non-metal. If it's covalent, it only contains non-metals, and if it's metallic, it only contains metals. So if we have a look at an example of a periodic table, you can see that I'm putting a zigzag in between boron and aluminium and going across and down. Everything to the left of that zigzag is a metal and everything to the right is a non-metal, with the exception of hydrogen, which is a non-metal. So all you have to do is have a look at the elements involved and you can then work out the type of bonding that's going on. So for example, if I have MgCl2, magnesium chloride, you find magnesium on the periodic table, it's a metal. You then find chlorine on the periodic table, it's a non-metal. So we have a metal and a non-metal, so we have ionic bonding. If we have a look at a second example, CO2, C you can see is carbon, carbon is a non-metal. O, oxygen, is also a non-metal. I've got two non-metals, therefore I have covalent bonding. And then the final example, Fe, iron, it's just iron on its own, it's a metal, therefore it's metallic. So now the examiner should be able to throw any two elements at you on the periodic table and you should be able to tell me whether it's ionic, covalent or metallic. The next steps is being able to draw the type of bonding and being able to explain the properties. So to be able to do that, we're going to move on into detail on each type of bonding. So we're going to start off with ionic bonding. Now, as we've said, it involves a metal and a non-metal, but what you also need to know is it's a metal that transfers or donates its electrons to the non-metal. So for example, I've got a metal here which has one electron in the outer shell, which means it's in group 1. It wants to lose that one electron. It's easier to lose it. The element on the right has got 7 electrons in the outer shell. It's a non-metal, therefore it's easier for it to gain one electron. So what will happen in ionic bonding is the metal will give its electrons or transfer them to the non-metal. And as a result of that, you end up with charged particles. These charged particles are called ions, which are atoms that have gained or lost electrons. Metals are always positive and non-metals are always negative. Now the definition for ionic bonding is the strong electrostatic attraction between an anion and a cation. An anion is a negative ion, try and remember that, and your cation, think cat, pause, positive. Now there is an easy way to work out the charge of all of your cations and anions, and to do that, what you want to do is have a look at how many electrons there are in the outer shell. So we're going to have a look at groups 1, 2, 3, 5, 6 and 7. We're not going to include group 4 because you won't be asked that in the exam. And we're going to have a look at the electrons in the outer shell, which you should remember is exactly the same. So what you need to now be able to do is figure out whether they need to gain or lose electrons and how many. So if it's in group 1, it's easier to lose 1 electron. Group 2, easier to lose 2. Group 3, easier to lose 3. Then group 5, it's easier to gain 3. Group 6, it's easier to gain 2. And group 7, it's easier to gain 1. So for groups 1, 2 and 3, which are losing electrons, they are losing negative electrons, so they become positive. So all metals make positive cations, and all non-metals are gaining negative electrons, so they become negative overall. Once you've known that, the charge is easy. So if it's group 1, plus 1. Group 2, 2 plus. Group 3, 3 plus. Group 5, 3 minus, because you've got 3 negative electrons added. Group 6, 2 minus, 2 negative electrons added, and group 7, 1 minus. So for example, aluminium is in group 3, it loses 3 negative electrons and becomes Al3+. Sulfur is in group 6, gains 2 negative electrons and becomes S2-. The next thing you need to be able to do in ionic bonding is to be able to draw it, and to be able to draw dot and cross diagrams. So we're going to have a look at the reaction between aluminium and chlorine. Aluminium is a metal, so it loses electrons. Chlorine is a non-metal, so it gains electrons. Therefore, we know it's ionic. So what we need to do now is draw out the outer shells of our elements. So, as we said, aluminium is in group 3. I put 3 electrons in the outer shell. Chlorine is in group 7. I put 7 electrons in the outer shell. Now I've done one as dot, one as crosses, so you know where the electrons have come from. Now, what you have to do here is you need to transfer as many electrons from the metal to the non-metal as possible, remembering you can only go up to a maximum of 8. So you can see I can only move 1 electron across to my chlorine atom. Now that chlorine atom is complete. I can show that by drawing it on the right hand side, putting a bracket around it, and putting my negative charge. However, aluminium still needs to lose 2 electrons, so the way to do that is you add another chlorine in, as you can see here. So we then transfer the next electron over to my next chlorine atom. Chlorine is now full, so I can move that over to the right hand side and add another chlorine atom to get rid of my final electron. So my final ionic configuration will look like this. It's really important to put the brackets around, to put the charges in, and to show what it was like before and what it's like afterwards. Now as we can see here, I've got 1 aluminium, I've got 3 chlorines, so I know my formula is AlCl3. I've gone through that quite quickly. If you're not sure, if you want more examples, have a look at my video in the playlist in the top right hand side. Now there's an easier way of finding the formula of ionic compounds. As long as you can work out the charge, it's really straightforward. So the first thing, you have to work out the charge. Remember, group 1, 2, 3, 5, 6, 7, charges become +1, +2, +3, 3 minus, 2 minus, 1 minus. So now you know the charge for any element in the periodic table that's in group 1, 2, 3, 5, 6 or 7. Now, if you get a transition metal, they will usually tell you the charge. They might give you it in brackets in the formula or the name. So for example, Cu2SO4 with the 2 in brackets tells you the charge is Cu2+. You also need to remember the polyatomic ions. So that's SO42- for your sulfate, OH- for your hydroxide, NH4+ for your ammonium, NO3- for your nitrate, and CO3-2- for your carbonate. Once you've got that, it's nice and easy to work out the formula. So for example, if we go with aluminium and oxygen reacting together to make aluminium oxide, aluminium is in group 3 and oxygen is in group 6. So aluminium is going to be Al3+ and oxygen is going to be O2-. So that's the first step. Step 2, swap the numbers. So get rid of the charge, swap the numbers, and then make them subscript. Now it's important to choose the numbers from the top, nothing from down at the bottom, especially if you have polyatomic ions. So if we have a look at aluminium and oxygen, I've got my 3+ at the top, so I'm going to take that 3 and I'm going to put it down here. And then my 2-, I'm going to take that 2 and I'm going to put it down here. So my formula becomes Al2O3. Now there are a few exceptions. If the charges are already the same, so you've got 2+, 2- or 1+, 1-, do nothing. So for example, Na+ and Cl-, the charges are the same, you do nothing, so it's just NaCl. And then the second thing, if you have a polyatomic ion, you must put a bracket around it if you are doubling it. So for example, aluminium reacting with a hydroxide, aluminium is 3+, hydroxide, as you can see up here, is OH-. I take the number at the top, I move it down to the bottom, but because I've now got 3 OH- polyatomic ions, I must put a bracket around to show I've got 3 of everything. Another example, ammonium, NH4+, reacting with a carbonate, CO3-2-. I take my 2 from the top right, I move it down to the bottom left. I've now got a 2 next to my 4. It looks weird, so I have to put a bracket there. So it's NH4 in brackets 2 CO3. The final part of the ionic bonding section is the properties. Now, nice and simply, ionic compounds have high melting points. They cannot conduct electricity when solid, but they can when they are molten or dissolved or aqueous. And the explanation for all three of those is all linked to the definition of the bond, which is the strong electrostatic attraction between your anion and cation. So why do they have high melting points? There's a strong electrostatic attraction between the anion and cation. Therefore, lots of energy is needed to break the bonds. Why can't they conduct as a solid? There's a strong electrostatic attraction between the anion and cation, so the ions are not free to move. They can't pass on a charge. And then why can they conduct when molten? Because those ions are free to move. You've broken that electrostatic attraction, so they are free to move. The next section we're going to look at is covalent bonding. So there are two types of covalent bonding, simple covalent and giant covalent. Now, when you take two nonmetals, so for example, I've got two chlorine atoms, we talked earlier that all nonmetals want to gain electrons. Now, if they want to gain electrons, they can't form ionic bonds because there's nothing there to give them those electrons. So what they have to do is they have to share them. And they do that by overlapping shared pairs of electrons. And that is your definition of a covalent bond, which is the shared pair of electrons between nonmetals. So as I said, there are two different types of covalent compounds, simple covalent molecules and giant covalent molecules. The simple covalent molecules only contain a few atoms, so CO2 has 3 atoms, H2O has 3 atoms, Cl2 has 2 atoms, C60 has 60 atoms. Usually if it's less than 100 atoms, we say it's simple covalent. Giant covalent has a lot, it has thousands of atoms. So for example, diamond, graphite and graphene. Those are the 3 main ones that you need to know for the exam. Okay, so we're going to focus on simple covalent first. Now, simple covalent molecules, as we said, they're tiny. They only have a few atoms. So their average size is 1 × 10 to the minus 10 meters, which is really, really small. Now, what you need to be able to do is draw the covalent bonding like we've got in the right-hand corner here for any nonmetals. So to do that, there are a few different steps. Number 1, you want to work out the valency, which nice and simply is how many bonds each nonmetal can make. So to do that, look at the groups for elements in groups 4, 5, 6 and 7. Find out the number of electrons needed to get a full outer shell, so to go up to 8. If it's in group 4, it needs 4 electrons to get a full outer shell. Group 5 needs 3 electrons, group 6 needs 2 electrons, and group 7 needs 1. The only exception to that is hydrogen. Hydrogen has 1 electron in the outer shell, but it only needs to gain 1 because that shell can hold a maximum of 2. Now, the electrons needed to get a full outer shell, that is the valency. That is the number of bonds an atom can make. Okay, now we've got the valency sorted, we need to be able to draw stick diagrams. So we need to figure out how we're going to put these atoms together. So for example, I'm going to react nitrogen and hydrogen together. Nitrogen's in group 5, and hydrogen, remember that's our exception, so it needs 1 electron. So it can make 1 bond. So as you can see down here, I've drawn my nitrogen and hydrogen with the correct amount of bonds coming out of them. Step 3, I'm going to put the highest valency in the middle, the one with the most bonds, which is my nitrogen, and then I'm going to put as many of the others around it as possible. So my small one is hydrogen. How many times can that fit onto my nitrogen? 3 times. So that's my stick diagram. Now I need to draw the actual covalent bonding. So I'm going to redraw it with circles overlapping every time there's one of those lines, as you can see here. Now each overlap should be a dot and cross. If there's a single line, it's 1 dot and cross. If it's a double bond or 2 lines, you get 2 shared pairs, so 2 dots and 2 crosses. Because my NH3 has only got single bonds, I put 1 dot and 1 cross in every overlap. And then my final step is I must make sure every element has 8 electrons in the outer shell, with the exception of hydrogen, which should only have 2. So I'm going to add in electrons onto the outer shell, not in the overlap, until I get up to 8 for everything other than hydrogen. So you can see for my nitrogen here, I've got 6 electrons. I need 2 more to give me my 5 crosses. Nitrogen should have 5 crosses because it's in group 5. If we have a look at a second example, carbon reacting with chlorine. Carbon's in group 4, so it makes 4 bonds. Chlorine's in group 7, so it makes 1 bond. So I put carbon in the middle and put chlorine around the outside. So straight away I know my formula is CCl4. The next thing I want to do is redraw with circles overlapping. So I'll put my carbon in the middle and draw 4 circles overlapping with Cl in. I've only got single bonds, so therefore I put 1 dot and 1 cross in each overlap. And then I make sure that everything has 8 electrons in the outer shell. Carbon already does, but my chlorines don't, so I need to fill them out to make sure they have 8. Now the only way this can become more complicated is if you have a double bond. So for example, in the reaction between carbon and oxygen to make carbon dioxide. So carbon is in group 4, so it makes 4 bonds. Oxygen is in group 6, so it makes 2 bonds. Now you can see here, because oxygen can make 2 and carbon can make 4, you join them up as many times as you possibly can. So it will look like this. So you're going to have carbon reacted with 2 oxygens and 2 double bonds between them. So I now redraw that with my circles overlapping, and because it's a double bond, I put 2 shared pairs in, so 2 dots and 2 crosses. I then make sure I have 8 electrons. Carbon's correct, oxygen isn't, so I fill them out. Now there are 2 major properties for simple covalent compounds that you need to know, which is they have low melting points and they do not conduct electricity. The reason they have low melting points is because there are weak intermolecular forces between the molecules. These weak intermolecular forces are nice and easy to break, so not much energy is needed to break them, giving them low melting points. It's important to remember covalent bonds are strong, so if you turn around and say the bonds are easier to break, you will not get the marks. You have to say weak intermolecular forces. And then why don't they conduct electricity? There are no delocalized electrons or no charged particles that are free to move, therefore it cannot carry or pass on a charge. Moving on to giant covalent compounds then. Nice and simply, these have lots of strong covalent bonds. Bearing in mind simple covalent only had a few, we've got a lot of covalent bonds here. This gives every covalent compound high melting points because lots of energy is needed to break those strong covalent bonds. Now the key examples of giant covalent compounds you need to know are all allotropes of carbon. An allotrope is something that's all made of the same element, carbon, but that has different structures. The main ones being diamond and graphite. So if we start with diamond, you can see here every carbon has 4 strong covalent bonds to them. This makes it really strong, so it's used in cutting tools. Graphite, you can see, is also made out of carbon, but it looks different, it has a different structure. Every carbon atom here only has 3 strong covalent bonds. This gives it a delocalized electron. That delocalized electron is free to move, which makes it useful in electrodes. The other useful property of graphite is it has layers. Those layers can slide past each other, and because they can slide past each other, they reduce friction, and therefore they're really useful as lubricants in cars. There are 3 other allotropes of carbon that you do need to know, which are nanotubes, graphene, and Buckminster fullerene. One thing that's really important is Buckminster fullerene itself is not a giant covalent compound. That has the formula C60, so that is simple covalent. But I've put it in here because it's an allotrope. Now all 3 of these allotropes have 3 strong covalent bonds. That means that all of them have delocalized electrons, electrons that are free to move, and therefore they all conduct electricity. So that's one important property for them. In particular in graphene, which is so tiny, so small, it can be used in circuits. Nanotubes are really strong. Therefore they're used in tennis rackets. Why are they strong? Because there's lots of strong covalent bonds. And then Buckminster fullerene, it looks like a football. What it can do is it can cage different drugs, so it's used in drug delivery systems. Okay, on to the next and final type of bonding, which is metallic bonding, which, as you should remember, is only metals. So the properties that you need to remember for metallic bonding is they have high melting points, they conduct both electricity and heat, they are malleable, which means they can be hammered into shape, and they're ductile, which means they can be stretched into wires. They are also sonorous, which means they make a ringing sound, and they have a high density. Remember, non-metals are the opposite to that, so they don't have a high melting point, it's low. They're not malleable or ductile, they're brittle, which means they break easily. They don't conduct electricity or heat, they're not sonorous, they make a dull sound, and they have low density. Now, of those properties that we've talked about, you need to be able to explain a few of them, and the way to do that is to have a look at the structure. As you can see here, I've got my metal atoms, and they have your positive nucleus. Now, when the electrons become delocalized, that positive nucleus resembles a cation. So you have a positive cation surrounded by a sea of delocalized electrons. Delocalized meaning they're free to move. This helps to explain the three major properties you need to know. Why can they conduct? Why do they have high melting points? And why are they malleable? So if we start off, why can they conduct electricity? This one's fairly obvious. They have delocalized electrons, they're free to move, so it can carry on a charge. If we move on to the melting point, there is a strong electrostatic attraction between your cation and your negative delocalized electrons. Therefore, lots of energy is needed to break the bonds. And then finally, why are they malleable? Why can they be stretched into wires? This again is to do with the strong electrostatic attraction. Now, because there is a strong electrostatic attraction between your cation and your negative electron, the layers can slide past each other. And what happens is the metallic bond doesn't get broken. So they'll stick together and can be hammered into shape. Okay, now we've been through all the different types of bonding, the different types of substance, we're going to bring it all together. So I'm going to give you a range of different chemicals and we're going to work out together whether it's ionic, simple covalent, giant covalent or metallic, and then we're going to use that to figure out the properties. So we're going to start off with lithium reacting with nitrogen. What I want to be able to do is describe and explain the properties and draw the dot and cross diagram for this compound. Remember the first step then, what type of elements do we have? Lithium is a metal, nitrogen is a non-metal, therefore it must be ionic. It's the only one that contains both a metal and a non-metal. So straight away I can say we have a high melting point, and hopefully you can remember from the video that's because of the strong electrostatic attraction between the cations and the anions, and lots of energy is needed to break the bonds. I can also say it doesn't conduct when solid, that's because of that strong electrostatic attraction, meaning the ions can't move, but it can conduct when molten, when a liquid, because the ions are now free to move. If we move on to the dot and cross diagram, it's a metal and a non-metal, so it's the transfer of electrons, so I need to know what group they're in to see how many they need to lose. Lithium is in group 1, nitrogen is in group 5, so I draw my outer shells. Lithium wants to lose 1 electron and nitrogen wants to gain 3. So I start off by transferring my electron from lithium to nitrogen, and as you can see on the right hand side, my lithium is now complete, it's got none in the outer shell, but nitrogen has only got 6. So I need another 2 more. So what I do is I add another lithium on the left hand side, I transfer that electron over, I can draw that second lithium in on the right hand side, as you can see here, which now gives me 7 electrons on my nitrogen's outer shell, but I need 1 more. So 1 more lithium drawn, transfer the electron across, then I can redraw my lithium on the right hand side. I've now got my 3 lithium ions complete and my 1 nitride ion. So my formula is Li3N. On to a second example. This time I'm going to have a look at sulfur and fluorine. What are the properties? Can I draw the dot and cross diagram? Well, both of them are non-metals. If they're both non-metals, it must be covalent. So I'm going to have a shared pair of electrons. So this time I need to figure out the valency. Sulfur's in group 6, fluorine's in group 7. Therefore, the valency if you're in group 6, it needs 2 electrons, therefore it can make 2 bonds, and group 7 can make 1 bond. So I can work out my stick diagram. Sulfur has 2 bonds, fluorine only 1, so I can join fluorine onto sulfur twice, and I'm going to have my stick diagram looking like this. Draw my circles with my overlaps, put a dot and cross in for every single bond, and then make sure I have 8 electrons. Sulfur now has 8, and fluorine's only got 2 there, so I need to add another 6 in, and the same on the left hand side. My formula is therefore SF2. Now when it gets onto the properties, we can see I've only got 3 atoms, 1 sulfur and 2 fluorines. Therefore, it's simple covalent. If it's simple covalent, it has a low melting point and it doesn't conduct electricity at all. The reason it has a low melting point? Weak intermolecular forces. You just have to remember that. If it has weak intermolecular forces, not much energy is needed to break the bonds. Why doesn't it conduct electricity? There are no spare, no delocalized electrons, no electrons free to move. Therefore, it can't carry or pass on a charge. Example number 3, diamond. Nice and simply, diamond is giant covalent, you just have to remember that. The other 4 giant covalent ones are graphite, graphene, and your fullerenes or nanotubes. So with that comes a high melting point. The reason they've got a high melting point is you've got lots of strong covalent bonds. And therefore, again, lots of energy needed to break those bonds. And diamond doesn't conduct, most giant covalent compounds don't conduct. Reason being, each carbon has 4 strong covalent bonds. Therefore, there are no spare or delocalized electrons. They can't pass on or carry a charge. Obviously, remember, graphite, graphene, nanotubes only make 3 covalent bonds, so they do conduct, but the majority of giant covalent compounds do not conduct for this reason. Example number 4, copper is a metal, only a metal, therefore it is metallic. Therefore, it has a high melting point. It does conduct electricity, and it is malleable. Again, just learn those facts, regurgitate them. Why does it have a high melting point? Strong electrostatic attraction. This time it's between the cation and your negative electron, and therefore lots of energy needed to break the bond. Hopefully you're starting to see a pattern here. Why does it conduct electricity? It has delocalized electrons. Those electrons are free to move, and they can pass on or carry a charge. And then finally, why are they malleable? Again, you've got your strong electrostatic attraction between your cation and your negative electron. Therefore, your metallic bond is not broken when you push the layers past each other. The next section of this video is going to look at how you can work out whether something is ionic, giant covalent, simple covalent, or metallic just by looking at the properties in a table. And also, how can you use an experiment to find out if something is ionic, covalent, or metallic. So there are a few rules that can help you figure out what type of bonding you've got. The first one I always start off with is, does it have a low melting point? If it does, every single time it's going to be a simple covalent substance. If not, it's either ionic, giant covalent, or metallic. So the next thing, does it have a high melting point and doesn't conduct at all? If it doesn't conduct a solid or liquid, it's got to be giant covalent. Just remember there are a few exceptions for that, which are your graphite, your graphene, and your nanotubes and your fullerenes. They will normally give you a clue in the question if it's going to be one of these 4 though. Number 3, does it conduct when liquid, but not when solid? If that's the case, it's always ionic. Ionic is the only one that will conduct when liquid, but not solid, because the ions are now free to move. And then finally, if it conducts both as a solid and a liquid, it's going to be metallic. Just bear in mind those exceptions, graphite, graphene, nanotubes and fullerenes, because they also conduct when solid and liquid. So let's have a look at an example table. If we start off with substance A, you can see we've got a low melting point and low boiling point. We don't need to look at any of the other properties. Straight away I can say A is simple covalent. Substance B, it's got a high melting point and high boiling point, so we know it's not simple. We then look at the conductivity. It doesn't conduct as a solid, it doesn't conduct as a liquid, therefore it has got to be giant covalent. On to C, high melting point and boiling point again, so that rules out simple covalent. It doesn't conduct when solid, that rules out metallic. It does conduct when liquid, therefore the only thing it can be is ionic. And then finally, substance D, high melting point and boiling point. It conducts when solid and as a liquid, therefore it's going to be metallic. So how can we do an experiment to prove this or to find out what type of bonding is going on? I would always suggest your first step is to heat it up, whatever your substance is. If it melts pretty quickly, it's going to be simple covalent. If it doesn't, it's got a high melting point, so it's going to be ionic, metallic, or giant covalent. If it's ionic, metallic, or giant, find out whether it conducts as a solid. So put it into a power pack with a light bulb in. If it conducts and the light bulb lights up, it's either going to be metallic or your exceptions for your giant covalent, which are your graphite, your graphene, your fullerenes, your nanotubes. If it doesn't conduct as a solid, it's going to be either ionic or giant covalent. Now, step 3, to find out whether it's metallic or not, can it be hammered into shape? Can you bend it? Can you shape it? If you can, it's metallic. If it's brittle and snaps really easily, it's going to be your graphite or your graphene. And then all we're left with is ionic and giant covalent. So, does it conduct electricity as a liquid, but not as a solid? So we've already said it doesn't conduct as a solid. All we need to do now is either melt it or dissolve it, put it into a circuit with electrodes, like your electrolysis, and if it does conduct, it's going to be ionic. If it doesn't, you're left with your giant covalent. That's all it can be. The final part of this video is having a look at the limitations of the different types of models we use in science, and there are 4 different ones you need to know, which are 2D models, dot and cross diagrams, 3D models, and ball and stick models. So if we start off with 2D, the advantages are they're simple. They show the atoms involved, and they also show how the atoms are connected together, as you can see the bonds here. The problem with them though is they don't show the shape and they don't show the size of the actual molecule. If we move on to dot and cross diagrams, the great thing about these is it shows you the electron arrangement, it shows you how the substance forms, and it also shows you where the electrons are from. But it also doesn't show you the size of the molecule, and it doesn't show you where the ions are arranged when you do ionic bonding. That comes in with 3D. So you can see here I've got my ionic lattice. It shows the ion arrangement, which is really useful. As you can see, it's a regular pattern where you've got positive and negative ions surrounding each other. However, it doesn't show you the size again, and it doesn't show you the insides. You can only see the surface. And then the final model, your ball and stick model, these are probably some of the best because it shows you the shape of the molecule, it shows you the arrangement of the actual atoms, and it's more realistic because it shows you that 3D representation. However, it's misleading. The bonds and gaps aren't actually that big. They're not actually there and visible like sticks that you can see on there. So it's misleading. And also, it doesn't show you the size. Now that really is it for the types of substance topic. Again, if you want more detail, have a look at the playlist in the top right hand corner. But hopefully you found this video useful, and good luck in preparing for your exams. Hi guys, thanks for watching. If you enjoyed the video, please click on like down below. You can also subscribe to my channel, you can check out the latest video, and you can visit my website up above here. Bye now.